So I'd like to start off this few minutes. I want to give you a picture of quantum. Both in 50 minutes, I'm going to jam in both the physics and the commercial side, just so you have a framework to think about for the rest of the afternoon. But I'd like to start off with a personal episode, a personal story. So I literally just this morning, I flew in back from the University of Chicago, where I'm collaborating with several people on building a new quantum device and a new type of qubit. And the collaboration includes University of Chicago, which I'm happy to say is my alma mater, University of Washington, Purdue, Copenhagen, and a couple of other places. And 5 years ago, something like this would have been very, very hard to pull off, where you have all of these cross-disciplinary folks across different institutions focused on quantum technology. And we've got a grant, we're hiring postdocs, the momentum is moving really fast. And another indication, which is probably one of the best ones about what's happening, University of Chicago never had an engineering school. In 135 years of its existence, it never had an engineering department, never had a computer science degree, and it has one, right? Sign of the times. It's the Pritzker School of Molecular Engineering, where a lot of this kind of quantum activity is happening. So, in the next few minutes, what is quantum? Just shifting gears to give you a framework, a couple of pictures to keep in mind. We don't have charts or anything, so I'm just going to wave my hands around. If you think about qubits, and every time you pick up the newspaper, you watch TV, I know there's a lot of physicists here, so this will be old news for you. But for those of you who are not physicists, the story you'll get about a qubit is it's not a 1 or a 0, it's something in between. So our conventional computers, what people would call classical computers, they translate all the information that we know into 1s and 0s. Current either flows or it doesn't. It translates everything to a 1 or a 0, called a bit, and then it manipulates the information that way. What is a qubit? So again, if you go back to the press, what they'll tell you is, most of the time, say, well, a qubit is like a dimmer switch. So it's neither a 0 nor a 1, but it's something in between. It could be like 0.1, 0.2, et cetera. So it's a continuous dial. That's not even accurate, entirely not accurate. A much better picture to keep in mind is, think about a qubit like the Earth, the surface of the Earth. And the North Pole is the 1, and the South Pole is the 0. And so what makes the qubit so rich and so interesting is every point on the surface of the Earth, between the South Pole and the North Pole, is the playground for the qubit. The qubit can sample and live anywhere on the surface of the Earth. And that's what makes these qubits so powerful. And it's computational power, okay? Because you've got all this extra information, and it could be built, this extra information could be built out of all sorts of materials. So you'll hear about superconducting devices, you'll hear about silicon, all sorts of mechanisms, atoms, charged atoms, neutral atoms, but they're all ways of implementing these types of qubits. And then you can imagine, once you have a whole bunch of these qubits, when they overlap, these surfaces of the Earth overlap, you can imagine the kind of rich structures that you'll get. So it's a huge advantage in computational power for some complicated problems that you get from qubits. But the trick, of course, which is why people are spending hundreds of millions of dollars to build these, is they're very delicate. They decohere. Anything in the environment could destroy it. So magnetic fields, for example, temperature, pressure, whatever it is, anything could destroy these qubits. And so the game is to try to trap a whole bunch of them and control them. But it turns out that we can actually use their sensitivity against them to our advantage as well. We can build devices that are sensors, for example, because these qubits are so sensitive. And so today, you'll hear about these types of applications. The picture that I like to keep in mind, and this is just going back to another analogy, very abstract. University of Chicago has, in the Pritzker School of Molecular Engineering, there is something called the Quantum Cafe. But I like to think about it, of course, you would expect students to create something like a quantum cafe. But I'd like to keep in mind a picture of a quantum kitchen. So what do you have in a kitchen? You have people in the back cooking up all sorts of interesting sauces. That's where the kind of this new breads, new sauces are happening. Then you've got the actual kitchen where people are putting together all of these wonderful ingredients into the dishes. And then, of course, you've got the front of the kitchen where people are actually eating. So you have folks here at NYU, for example, who are deep in the weeds in the back, creating all of these beautiful qubits. For example, like you'll hear from Javad. And then you've got people who are putting together these applications into sensors using these qubits for sensitivity. And you hear from a couple of folks here, Noel and Amanda, from startups who are doing these things here today. So then you get into the front of the kitchen, and it turns out that people are actually paying for these services now. They're beginning to pay for some of these calculations. For some of these devices, telecom companies are looking at using these qubits, for example, because of that all that rich information structure, moving that information. How do you get advantage from moving this extra information, all of these surface of the qubits between 2 points? Right, so telecom companies are looking at it. Sensor companies are using these qubits. Just one example would be, remember I said that they're sensitive to magnetic fields. Well, it turns out, for example, GPS requires satellites. If you knock out a satellite, you can't use GPS. But you can use these types of qubits to navigate on the surface of the Earth according to the changes in the magnetic field. Okay. Then you've also got sensors now where people are looking at using these magnetic devices for more sensitive MRI. So there's a lot of these types of applications that are beginning to get rolled out. Some of these MRIs, these enhanced MRI techniques are already in human trials, for example. People are beginning to pay for some of these types of sensors, deploying them in different environments. So all of these things, like going back to the original picture, oh, and here's Juan, you'll hear a lot from Juan here. I was just talking about University of Chicago, and we'll talk about all of these wonderful things happening in New York in particular. There's a lot of centers right now in the US. So Chicago is a center for quantum, Colorado is a center for quantum, Montana is developing one. It's kind of burgeoning all over the place, and folks here at NYU are building a center here. And so you will hear about that as well. This full suite from the kitchen, again, coming back from all of these nitty-gritty exotic devices to putting them together into applications that people are using, to customers who are actually using them and harnessing them, and organizations that are popping up to take advantage of all of this infrastructure. And so as far as timeline, my own view, I'm taking the approach of a commercial approach to this. So we're looking at it as a science, but it's also not a science project, right? So for me in particular, I've been at hedge funds for the last 15, 20 years while doing the physics. And so I also have a commercial hat thinking about these things. And 5 years ago, just like for University of Chicago, 5 years ago was too early to have an engineering department, or maybe a little bit more than 5 years ago. And 5 years from now, given the pace of innovation and the types of groups that I said are popping up, like the cross-collaborative group that I'm working with, 5 years from now will be too late. So that's really the way that I think about the intersection of the physics and the commercial aspects. And so with this, I'd like to hand it off to Juan and Javad to tell you about all of the really exciting things going on here at New York.
Thank you very much. It's wonderful to be here. Thank you for joining us at NYU. Every few years, a new idea comes along, a new technology, with the potential to change the way we live and really impact our lives. These technologies, these ideas, not always emerge in a single shot. It is a series of cumulative events that all of a sudden, when put together, represent a new technology. Examples are the transistor, CRISPR, AI, and now quantum. Sometimes, like for the transistor, those technologies emerge and we're not even noticing. Sometimes they emerge and we're not ready to take advantage of them. That is the example of AI. When 20, 25 years ago, when the ideas first came up, we were not thinking about the potential of the technology. And now we have quantum information sciences. And I think this time is different. Quantum can really alter communications, sensing, navigation systems, defense, computing, in ways that are going to be profound and dramatic. And this time is different because I think, given the lessons from the past, we're ready to take advantage of the opportunity. To take advantage of the opportunity, you need to very quickly assemble the right talent. You need to very quickly create the laboratories, the infrastructure that allows you to produce the devices, the materials, the components that will fuel those technologies. You need to take advantage of the ecosystem around you and make sure that the investors and entrepreneurs are embedded within these laboratories, within the conversations, to make sure that when a great idea comes up, you can immediately bounce and turn that into something. This is really what this meeting is all about. It is to tell you about the promise of these technologies, how they work, what they can do for us, and make sure that all of you are aware of what's happening at NYU and other places in the city and the state to make this really a thing that benefits us all. It is in that spirit that we're announcing publicly today the creation of the NYU Quantum Institute. With that, we will make major investments, well in excess of $50 million in the first phase, to recruit new faculty, recruit students, attract companies to work with us, and most importantly, create the spaces, the laboratories, the core facilities in which our researchers, our inventors, will be able to develop these technologies. I think New York State, as a state, has a lot to offer in this area. We have great elements in the semiconductor industry, fabrication facilities, national laboratories, Air Force laboratories, many universities at the forefront of this technology, NYU very much in that place. I think it is an opportunity that is ours to miss. So with that, I'll invite Javad to tell us a little bit about what these technologies do and what we've done up to this point. Javad.
Thanks. Okay, it's a pleasure to be here. And so I'll tell you a little bit about, I guess, quantum at NYU and how we look at it. If you have been following the field of quantum, for a century almost, we have been trying to understand quantum, looking into the stars, looking into atoms, looking at the molecules, right? Trying to really discover new things, and there has been many Nobel Prizes for the discovery of this or that, right? And it's been extremely fruitful. And the way that you should think about it is that we have become so good at it that we can now dare to take hands in there and start manipulating things. So the original discoveries of Schrödinger and Einstein and Dirac, and so we can call them first quantum revolution, or quantum 1.0. Things that we discovered in the world around us. But now we are kind of transitioning into this new era that we are trying to kind of use those things to do something for us, right? In terms of computing, in terms of communication, in terms of sensing. And this is where it makes it super exciting. So it's not that it's just another field. It's really in the world that we are living in. We are trying to kind of be brave enough and ask questions that have not been able previously asked or answered. Like, when you get, 101 quantum, the quantum mechanics, they tell you atomic hydrogen is a quantum object. And when you get classical mechanics, they say an apple falls down the tree is a classical object. But you never know, is there a line in between that separates classical from quantum, right? Indeed, there is no line. If you go to TSMC, N3 node, they make 3 nanometer transistors that are pretty much working classically, I would say. I mean, you have to know quantum effects, but it's really the same rules of electron, the currents and voltages. If you ask the opposite question, you can also say, how big of an object I can make that is still quantum? Is it like angstrom? Is it like nanometer? Is it micron? Is it millimeter? Can it be a meter? The answer is that it can be as big as you want. Actually, you can make meter-sized objects to actually be fully quantum mechanical. And these are the kind of fundamental science that people have put a lot of effort, in terms of creating these artificial quantum atoms. And actually, this year in 2025, this macroscopic quantum effects got the Nobel Prize in Physics just last week or so. That really highlighted how we have excelled at our understanding in quantum physics. So the next thing now is that, okay, now that we have such a level of control, can we actually make a quantum computer? Can we make a quantum communication network, right? And this quantum 2.0, or the revolution that is happening around us, has already manifested, I would say, in the last decade or so. When I was a postdoc at Harvard in 2009, 10, my project literally was to go from 1 qubit to 2 qubits, right? And it was a very difficult project. That has changed now. I mean, Jerry, who will talk later, can tell you that there are hundreds of available qubits that you can have access to right now, today, from IBM and other, basically, technologies, big techs out there, right? So the field is changing. We are getting that level of control with tricks, not exactly doing the hardware. We are not, I mean, you can get atomic hydrogen to be a qubit, but now we are making these new things that we can fully control, right? So that's super exciting. I think the role of the university, at least at NYU, we are at the heart of the city. We are where all the end users are going to be for these technologies, right? We are doing the innovation. I mean, as one said, we have maybe 100 years, actually, history in quantum mechanics, as well as the determination to actually making it happen and be part of the second quantum revolution, right? But obviously, there are traditional ways of doing things. When I was a student, I read books. Ashcroft and Mermin is a very well-established book written in 1976, which would describe topics from 1950s and 60s, right? But those would not help me to kind of make a qubit, right? We need to kind of evolve our education with what actually we want to do, right? So we need the books for 2020 to prepare us for 2030. Right? And that's where I guess this kind of unifying university, industry, government labs, and policymakers that have to come together to create an environment that actually is fruitful. You also want to see the result. And the near-term results is where actually the action should happen. And I think New York is a fantastic place for that. At NYU, we have a very long history of actually launching startups in different sections, including quantum. And the other thing is that the finance world out there, the insurance world out there, all of these are the fields that the quantum would directly impact them. Whether it's a medical sensor or whether it is a security, whether you like Bitcoin or not, these are the things that quantum can actually change and can have an impact. So to just give you a picture, and I will wrap up with that, is that it's kind of a funny discussion, but I think it's kind of interesting. That what is quantum, where are we, how is it going to change our life, right? And I was watching a Star Wars with my son, and there is this photo of a starship that kind of basically gets all this display, and he said, like, it would be cool if we had one. I was like, yeah, it would be great. And he said, like, if you had one, what do you do with it? I'm like, I don't know, I will go to another galaxy maybe. And he said, which galaxy? I'm like, I really don't know. I don't know what is out there to go explore. And as I'm talking, it kind of like, I feel like this starship is actually quantum, right? It's something that, it's amazing. It has, powers that no other airplane has, right? That you can go places that nobody else is able to go. Maybe we don't have the hyperdrive engine right now. Maybe we don't have the shield that we need to go through the outer space recent, right? But it can have it. We have seen it, right? We have seen that all this complex system is actually out there to really become something that you can explore the outer universe or whatever, the galaxies. And those are the applications that we want to be. But first, we need to know what those applications are, how important they are. And it could be that it's really important for humanity, right? It could be important for, I don't know, you want to have a tourism thing. Like, it's very different in terms of the application and the impact, and we need to explore those applications. We need to contribute to how we actually make it more powerful. And as an academic, I think these are the things that we can do. Like, I think it would be not the proper, our effort to kind of at the university make a Starship, but we can definitely work how to make a better hyperdrive engine, right? And then there are other people who can actually put it into a system to go out. We can definitely look at, you want to go to another galaxy right now. Peter Scholl tells us, oh, you can hack the internet. It's fantastic, right? But we have to also develop it and show it and then kind of realize all those promises. So I think these partnerships are very interesting. It's developing. It will come a day that we can do a jump into the space. And I'm really excited myself. There were the same kind of questions that, is quantum real? Is it going to be anywhere 12, 15 years ago when we had 1 to 2 qubits? And back then, there were still believers and non-believers. If you just look at it, the amount of progress we have made in the last decade or so is faster than the Moore's Law, which is shocking to me, right? Because when I was a student, every talk would start with Moore's Law, and you would just be shocked by that. And this is really kind of credit to all the brilliant people working in this space. And I can tell you, all the students that come to NYU come to academia. In the old days, we were always making a joke that, Condensed matter really uses people who want to do black holes, and then they come in and then switch to condensed matter. But now, quantum by itself is super exciting, like, teleportation, entanglement, distribution, things that you cannot really imagine being able to do, but now we can imagine. Now we can actually do it in the lab. We can teleport photons between, Brooklyn and Manhattan with our colleagues here. So these are the things that you would think these are fairy tales, but it's happening. And as Juan said, I think we are at the very exciting point in quantum, in particular in New York City, that where applications can be tested, and we are really proud that we are at the forefront of that. So with that, I will thank you.
So why don't you grab these two over here? Can you hear me? Testing. So thank you. I'm going to take off my science hat, take my other hat, put my investor hat on. And all of this really cool stuff that we just heard about, we are going to now hear from people who are practitioners, from people who are creating products that people are investing in and interested in investing in. And people wouldn't be investing if they didn't see a return on this investment. And that ultimately is what's really exciting. So can you please introduce yourselves?
Hi, everyone. My name is Amanda Stein. I am the CEO of Quantum Catalyzer, and we are a research and development organization focused on quantum sensing. We're based out of the Washington, D.C. area, and specifically College Park, Maryland, where the University of Maryland is. And we work on the research that then will spin out into, hopefully, investable companies.
Hi. Is it working?
Yes.
Yeah.
So my name is Noel Goddard. I'm the CEO of QNect. It's a quantum communications, quantum networking startup company headquartered in the Brooklyn Navy Yard. We started as a spin-out of Stony Brook University, but in the last 5 years have actually put together a full stack quantum networking solution, which we've now sold to a number of both universities and industry labs and also government labs in order to support the distribution of entanglement over standard telecom fiber. It's an interesting new part of these quantum domains, which sensing and networking are the lesser known verticals in the quantum tech space. But what quantum networking's large potential is actually to enable the scaling of other quantum technologies. You can think of it exactly like the internet of today. When computers were isolated, of course, they could solve important problems. As we started to actually be able to network them and start to explore things like distributed computing, things became more powerful. I think the quantum computing industry is starting to acknowledge the need for networking in order to scale to larger numbers of qubits, to be able to actually support harder problems. Also in the sensing community, the idea of being able to build distributed sensing networks is also of interest, so networking is at the core of that.
Thank you. So let's drill into a couple of specific applications. So Noel, you have recently been rolling out a product to detect eavesdroppers. You might have heard about quantum communication as a battleground, a geopolitical background. So people are doing harvest now, decrypt later, for example. There's people who are routinely eavesdropping on our current signals. So can you please talk about that application or any other application that specifically just for this audience as an introduction?
Thank you. So I think one of the ways that we always think about how is quantum going to actually become real and used, so in the real world scenarios as opposed to just something in the laboratory, is when it provides quantum advantage. And quantum advantage in quantum communications is largely around security use cases at this point. And what's interesting is that it's actually more of a sensor application. So if you can think of a quantum network as a giant sensor, if you can actually create a system that is ultra sensitive to detecting eavesdroppers, that's a good way to add a physical security layer over the existing digital communications infrastructure. And the way we do it at QNect is basically to find a way to distribute entangled photons so well over the existing fiber beds that any disruption of those becomes a disruption of the entanglement itself. So you use them as check bits effectively at the other end. And we've been working with government partners in order to be able to build this system with our existing network stack. It's just the first of many different types of applications where, again, the advantage is that it integrates with the existing digital today. So you have adoption because it's not trying to replace what's actually there with completely quantum systems, but it provides enough advantage to continue to produce a sort of need in the industry for something which has a justification of cost, right? So quantum technologies, as we all know, require a lot of fancy equipment. Even in our case, where everything is done at room temperature, you still have to purchase the CapEx expense. So it has to be something that truly provides enough advantage to drive that piece of technology forward and to drive down the cost eventually.
Yeah, and just putting my science hat back on, it's just the progress in the last 5 years is incredible. Like 5 years ago, people didn't know that you could take a quantum signal over a regular, or they theorized that you could, but nobody had built one 5 years ago, right? It was only like in the last couple of years that you can use existing networks to transfer quantum information on. So dovetailing into the sensing, I know at QCAT you guys are developing what are called rugged sensors, because these qubits are, as I said, they're very, very sensitive. So to be in a real environment, they have to be rugged and withstand all sorts of pressure, temperature. And I know you guys are known for working on diamonds, for example, and leveraging the hardness of diamonds. So can you talk about that application?
Yeah, and I will say these are specific, special lab-grown diamonds that are grown with a vacancy so that when light is shown, it tells information that excites quantum properties that are able to be highly sensitive, be able to tell different pressures, different temperatures, and then because of this, and because diamond is such a robust host, I mean, come on, diamond is forever, right? That this robust host is able to go in robust environments, and environments that, as Javad was saying, where sensors don't go right now and where sensors have never gone before. So think about up in space where there's a lot of radiation, or going down in a downhole drilling, or up even in a power lines or in the transformers. What I learned through this is that there is no sensors on current power transformers. So all of New York City right now, we don't necessarily know when the next power transformer is going to blow. So with a ruggedized quantum sensor, something that is room temperature, that you're able to detect the high temperatures or high pressures put on different these sensors on power lines or transformers across the world, you're going to be able to say more about what's happening on the power grid. Now, this also provides more information, and we keep hearing about AI and how important AI is now, but we can't have AI without data. So with more data coming from quantum sensors, not only the rugged ones, but from quantum sensors like Noelle was talking about, or quantum sensors that could potentially sniff if your food is going bad. There's lots of applications, but the data that's going to be coming out of these quantum sensors are really what's going to be moving the needle.
Thank you. Noelle, just abstracting it slightly from from one application, how do you see these kinds of business models, in particular in networking or choose a field in quantum? How do you see these business models evolving in its early stages?
It's only funny because quantum has this problem that it is a long horizon tech, right? So business models evolve, I think, probably at a faster rate to try to tap what's interesting to investors and what looks at that point like it's going to be a near-term market. So for QNect, we build hardware. And that's traditionally not a really simple venture gambit, right? Particularly if the hardware that you're building is expensive. And quantum compute is not that different, right? So if your quantum computer costs $25 million, you know what customer base you're talking to, right? But in our case, when you start talking about quantum networking, it's a little bit of the same market, because right now, if the advantage for my quantum technologies is enhanced security, think of who are your security-sensitive customers. So, of course, on the government side, government and defense is a natural one. Those are customers that actually have a different risk profile than private customers like finance. Critical infrastructure falls somewhere in between. And I think what we've been seeing right now, at least with service providers, is that there's a lot of curiosity, but almost all service providers are providing a service, right? So there's the service model of who would pay for quantum if you were going to establish it today on networks. So what we've been doing as a company is to have a lot of strategic partnerships with the finance industry. That's obviously very security sensitive. So we have ongoing projects with finance in order to test out protocols that would have some advantage of their existing transaction systems. We have other partners like Deutsche Telekom that we work with as a service provider who are trying to do things like entanglement as a service and to see how quantum and classical can actually coexist on networks like the network they established with our equipment in Berlin. And they're testing effectively what would a market opportunity be, how stable are these things today for actually offering this type of opportunities. So I think what we have seen, and we've seen this across a lot of industries now, that basically strategic partnerships open up the opportunity to think of what the market actually could be, but existing customers today are largely government.
Thank you. And Amanda, same question on business models in the sensing world.
Yeah, and just like Noelle was saying, we're actually looking quite a bit into the service model. So we also build hardware. Granted, our hardware is a laptop bench instrument in some cases, or a sensor like what is in this microphone, eventually small little sensors. So don't need as much room or space, and the cost of building a quantum sensor, at least from the nitrogen, vacancy, and diamond, is a lot less than building a quantum network. So when we're looking into how we're eventually going to make money, and make money for Demetria and Quantum Coast Capital, we are thinking about both a hardware model, what is the hardware that we can sell? We're thinking about a service model with what can we license, what can we actually service, and the consumables that are involved with that. But then we're also thinking about what do we have in our lab now that we could potentially make money off of. So could people come bring us an object where they're looking for very small magnetic signals, and you're asking what has small magnetic signals. So there is magnetic signals pretty much everywhere, and one of the applications that we've started exploring and that we're going to make hopefully money off of in the service model is high value objects. So paintings have magnetic properties coming out of the paint that is in a piece of artwork, and we're thinking about a model where people can bring artwork to us or ship artwork to us that then we are able to detect the magnetic properties where the paint might be degrading, or where there might be a hole in the canvas, so that we can then tell different information. And then of course this goes back to data, and just like we know, you can always sell data.
So which sectors would excite you the most? Like in general, where do you think some of the biggest opportunities in sensing will be, let's say, 5-7 years from now?
So one of the biggest areas that we're working in is in validation of next generation chips. So if you're familiar with the semiconductor and world, and Javad talked about Moore's Law, is moving beyond Moore's Law, so chips are being slowly packaged vertically instead of what they were before. And there are no tools right now that are being able to look into these packages non-invasively. So we're very excited about this tool, and this is one of our spin-out companies called Euclid, of course with a Q because we're quantum. And so I'm really excited in the next even 2 years, I see this going in line into semiconductor production that's able to detect where there might be problems within chiplets.
Excellent. So bringing it back even before 2 years, Noel, I think maybe for this audience, for those who are not familiar with, maybe you can describe the network that's already running in Gotham City.
New York.
In New York.
So appropriately called Gotham Q. When QNET got started, we knew that we wouldn't be able to convince anybody that we were building something for the real world unless we rented existing commercial grade fiber somewhere.
And you had a Q in it.
It had a Q. So we needed to rent fiber someplace in order to establish a network. It was only natural because of what we've heard today about finance being obviously hubbed in New York City, et cetera, that if we could build a network in New York, that we'd have the opportunity to have these collaborative partnerships, which we have now. So when we raised our Series A round, we were able to establish the first loop of the node, but it was still the supply chain delay years, so we couldn't actually supply extra nodes on the network, so we looped back to ourselves in the beginning. So the first loop was through Brooklyn and Queens. Then secondly, we established an industry partnership with Javad and the Center for Quantum Information Physics here at NYU. And our second node became NYU, so then we established the fiber between that, again rented from a commercial fiber company. And eventually we wanted to also integrate into a data center, so there's a historic building down in Tribeca called 60 Hudson Street. It's the original Western Union building. We now have a rack of instrumentation there, so this was expansion piece by piece. Now Columbia is connected to us. Now we also have fibers running to Stony Brook and to Brookhaven National Lab. So it's the beginnings of a network, and if you look at the very early maps of ARPANET, it really emulates what people were seeing in those
Totally.
years, right? With nodes of academic researchers and government researchers playing together on a new network.
Completely, and I actually think that we've learned a lot in deploying the classical networks, and so this cycle will be quicker than the pre-.com cycle, the initial one, because of all of this information and learnings that people can now leverage. So just to close on another question, what do you see are the biggest challenges to adoption? And this is a question for both of you, one to sensing and one for networking.
Yeah, as far as challenges go, I think not doing anything right. And I say that because if you're going to do something, do it well and do it right. So don't just think about it as we're going to put a little bit of money in it and we're going to do just one project. We're going to think about it as a whole suite of systems and how these systems can affect real applications, and actually fund it at levels that the actual hard research needs.
This is always, I suppose, as the two lesser industries behind quantum computing, right? Funding is always a really big one, and that's the do it right part. I would also say advantage. So really having the ability to show that our industries can bring advantage is harder, and traditionally quantum networking, because it was in the security space, plays in a very rich field of digital solutions. So being able to offer that there's something above and beyond that will drive adoption is, I think, it's always a big challenge in that piece, and then funding is obviously huge.
And as far as the adoption, there's some of your partners and some of our partners don't necessarily even care that things are quantum. They care that we can do things that haven't been done before or can do things better than what's currently out there. So I think specifically for quantum sensing and networking, we're judged differently than quantum computing companies, and more in line with traditional telecommunications or traditional sensing companies.
Definitely.
So I think this is perfect. Thank you. I think we have 2 or 3 minutes for Q&A. Any totally optional? No? Okay, perfect. So we're going to move on to the next one. I gave everybody about 1 microsecond to respond.
Thank you guys. Great. Come on. Thank you guys so much for that. So, first of all, NYU, thank you so much for hosting us today. It's been such an honor to work with you guys throughout this process and really shedding more light on quantum and activities that are happening within the quantum ecosystem. I've been very fortunate over the last year and a half to meet many people within the quantum community. And one of the things that I always tell people is quantum has a communications problem. And the fact that there isn't enough information out there that's accessible and also digestible for the general public. There is so much incredible activity that's happening within this community that, again, my hope through these events that we've been doing throughout the year is to shed more light on really an exciting area and an exciting ecosystem. So that said, I'm Matt Smaglia. I'm the founder and managing partner of Quantum Coast Capital. And we are aiming to really invigorate the quantum community and the ecosystem through investments. And that being said, Jerry, I'll let you introduce yourself.
Yeah, hi, my name is Jerry Chow. I'm an IBM fellow and the director of quantum systems from IBM. And I'm responsible for all the work that goes into deploying real quantum systems that are available and accessible over the cloud. I wonder how many of you actually all know that they are already available and accessible. But also, building that as part of an overall view of how your future of computing is going to involve quantum, right? In addition to all the other things that you already use, like GPUs and CPUs, in something we call quantum-centric supercomputing.
Hi everyone, my name's Lamont Silvas. I'm with IonQ. We're a company that's headquartered in College Park, Maryland. We were spun out actually from the University of Maryland to commercialize some Nobel Prize winning work that was done by a gentleman named Dave Wineland with our co-founder participating, Chris Monroe. And we've been in business about 10 years. I'm head of government solutions. I've been with the company for roughly 3.5 years. I'm not a physicist and probably couldn't even play one on television. But what I can do is describe the importance of quantum technology for national security and for business as the world evolves. And quantum is moving very, very rapidly today, and I'm looking forward to this discussion. Appreciate you, Matt, hosting this, and certainly appreciate NYU inviting us to speak. So thank you.
Thank you. So Jerry, by the way, he has a great article about his work at IBM in the Wall Street Journal from about a month ago. Congrats on that article. After that, I'm sure you were at various dinners and dinner parties where you had to actually explain to people what is a quantum computer. Again, in the spirit of understanding and being a little bit more generalist on this conversation, what is a quantum computer?
Yeah, you got it. And it's one of these discussions that obviously you can dive into the physics part of it, and all of a sudden you're stuck, talking for maybe an hour, right? And obviously we don't have that time. But what I like to say really there is that think about the quantum computer as a way of processing data entirely differently than you're used to with your traditional computers. Obviously, we work with bits, right? Zeros and ones. Instead of bits, we work with qubits. You might know also in computers, we work with digital circuits, right? Which have operations like AND gates and NOR gates and NOT gates. There's a similar different language of operations that run on quantum circuits. So the ideas of entanglement, superposition, the physics stuff that you hear about, Einstein and so forth, those change the rules by which these quantum circuits fundamentally operate, which lets you calculate certain things which are beyond what you'd be able to do with just classical digital circuits. And really that's the differentiating piece. That is a different set of math that you can handle specific types of problems in ways that you would not be able to do with regular computers.
So as a sort of follow-up to that, give me a tangible example. And a little bit of that horizon.
Yeah. So things like simulating molecular structure. It was talked about a little bit already, in the sense that did you know that the world's most powerful supercomputers, most of the time that's spent on them is to actually perform approximations of getting things such as energies for molecular structure, for designing drugs and so forth. All these things that are important in terms of materials really is something that now, because of the quantum mechanical effects that govern how electrons behave and so forth, it happens you can also map that onto a quantum computer for exploration.
So Lamont, IonQ is very different, obviously, in its ion trap systems. Explain to me a little bit about what that is, first of all, and also its ability to scale and why that's so important.
Sure. So the approach that we take is fundamentally different in many respects from our friends at IBM, because what we do is essentially trap ions and manipulate them to compute. We do that using, today, lasers, in the future, most likely chip design, which will eliminate the need for the lasers, many of the lasers that we use today. But it's a very different way of doing things. We think, with a great deal of respect to our colleagues, because we're all advancing the field, we think this is going to scale more readily for a couple of reasons. One, it doesn't require a lot of cryogenic cooling, because we're only cooling the trap. And the chip, if I had one with me, I'd show it to you, but it's essentially the size of my thumbnail. And that's essentially the space that we need to cool with lasers. So we think that will help with scalability. Importantly, also, these qubits that we're trapping are essentially perfect in their nature because they're naturally occurring. We're not building a qubit, we're trapping an atom. So again, we think this is going to help. That said, I would say to you that we all have a lot to learn, and we'll all learn a lot of lessons as we move forward, and probably the best thing that we can do is learn from each other, because we all gain by advancing the science.
So Jerry, you touched a little bit on the cloud and having access on the cloud and that it's already kind of here, but I think this is a question more to both of you. Like, where are we with accessibility in the cloud? And also, when is there going to be a time period when businesses can start actually using quantum as opposed to just the research phase?
Yeah, so we at IBM, we work with superconducting qubit technology. They need to be cooled down in dilution refrigeration, dilution refrigerators to lower temperatures. That's part of the discussion we just had here. But for a long time, it's a very, very physics type of experiment. But in 2016, we took the leap to actually put something on the cloud, and we made it accessible so that we had to start to build levels of abstraction on top of it, so that it didn't appear as a physics experiment. It appeared as something that you could actually program and compute with. And over the years, we've developed a lot of the layers of the software stack and the accessibility to really make it a really full-blown cloud accessible service. Now, today we have roughly 10 systems that are hosted online that are over 100 plus qubits. Right? These are quantum computers that are sitting in data centers, both in Poughkeepsie, New York, and as well as in Germany with our EU data center. And we have so thousands of users who are accessing these, making research, publishing papers. Over 5,000 papers have been written with our access since our inception of 2016.
Right, it's similar for IonQ in the sense that we have there are three different ways fundamentally that users engage with our hardware. They can go on to any of the three public clouds, Microsoft, AWS, Google, create an account, submit a query, submit an algorithm, get a result. That's really great for research, and it's being used today by researchers all over the world for that. That's one way. The second way is they can buy time on a system that we host for them in our primary data center in College Park, Maryland. And so What the Air Force, for example, has done is buy a percentage of the uptime of one of our systems. We host it in a private cloud, make it available to them and to users who are working with the Air Force on that. AFRL is our customer for that up in Rome, New York. And then the third way is they can actually buy a system. And that's our largest customer for that is here in New York. It's the Air Force Research Lab, again, up in Rome. And then we also have an EMEA data center located in Basel, Switzerland, for our friends and colleagues in Europe and the Middle East who are working with us on that. So those are the three ways today that most people engage with IonQ on this. And the thing that I would add, there is such critical importance in what IBM is doing, what IonQ is doing, what Amanda is doing with her company, what QNect is doing. We're building hardware. These are difficult, challenging, capital-intensive things to do. And it's great that we're all doing it, because the risk we face as an economy here in the United States is that we do this full transition from doing tough engineering work and building hardware to becoming the world's software house. That's great for a time, but then eventually you find yourself in a position that, not to call anybody out, but the UK finds themselves in today, which is they lose a manufacturing base and all of the skills and the capabilities and the investment needed to do that kind of tough manufacturing. This is not to take anything away from some of the folks there. We acquired a company in Oxford recently. They're doing really great work. But it's so important for us as Americans to actually do the work to build hardware.
Yeah, I wanted to touch back on the enterprise use cases and everything there, right? So certainly, we're driving a lot of adoption in terms of enterprise, as well as obviously in the scientific community with national labs and so forth. A big part of that is that right now we're at a scale with these systems at 100 qubits or so, where you can run circuits on these machines that you cannot simulate classically. Now, this isn't at the level of the proven advantages that we know that we expect quantum computers to be able to be used for. But we're in a phase where they can be leveraged to explore these use cases. And for example, we had results from HSBC and Vanguard recently looking at things such as bond pricing and portfolio optimization, really starting to push the limits of things which are traditionally challenging for classical computers, but now they have a different tool, right? And think of it as a tool in your chest. It's not there to replace all your classical computers. It's there really to augment your other workflows, your traditional computing workflows, especially as you're developing and evolving with other things such as AI. Now you need to make sure you have a quantum element to how you're evolving your compute platform as well.
So to tee up my next question, Jerry, explain to me, and again, we've had a couple terms today that we've been throwing around and saying, what is a qubit?
A qubit is a quantum bit, right? So everyone knows what a bit is, zeros and ones. A quantum bit is two states as well, except they happen to be quantum mechanical states. So they actually follow the laws of quantum mechanics, which means that they have these properties in quantum mechanics like superposition, uncertainty, right? You've heard of an uncertainty principle. So you have to measure them. If you're in a superposition, you measure them, you force it to choose 0 or 1. So the fun thing about these qubits is that even though they have these states like that are superpositions or entangled states that are unrepresentably classically, when you measure them, you force them into your classical computer, and you still see them and experience them as zeros and ones. And so it's really leveraging that kind of underlying mechanism of how information is different, right? That gives the potential for an advantage in specific computations.
So on that note, Google published a paper a few years ago, and they essentially went into RSA encryption, saying that they would need approximately 20 million qubits in order to break RSA encryption. And about 3 or 4 months ago, Google comes out with a new research paper saying they've further optimized it. And again, we've been talking about Moore's Law a little bit here today, in that quantum is much faster than Moore's Law is being tracked. And this paper basically said you can break RSA encryption with 1 million qubits. Lamont, we were talking about Shor's algorithm earlier. What does that mean, not only just from a global perspective, but from a national security perspective?
So I'll talk about this from two different perspectives. I spend a lot of time on the Hill talking to folks who understand national security really well, but may not understand quantum technology very well at all. And what I say to them in this regard is two things. One, cooperation around the world with our colleagues in other countries is so important. And I really urge them not to make the US a quantum island, because there's a tipping point, right? There's a point at which we want to secure our intellectual property from theft or from others who don't maintain the same standards of protection that we do in the US and in other countries. But if we wall off the US from that kind of important international collaboration, we lose those advantages that we gain from working with other folks in other countries. That said, Shor's algorithm is so fundamental to national security and what it means, and we're moving very rapidly towards a time where we or IBM or others who are building this hardware are going to be able to implement Shor's. And it's going to happen, Q-Day is the term that's used a lot. That's going to come before a lot of people are ready for it. And I'll give you one example. NIST is requiring agencies to be prepared for that by 2035. I'll put a stake in the ground right now and tell you one of us is going to get there well before 2035. And when that day happens, we have a real problem, because the issue doesn't begin on that date when Shor's gets implemented. The issue is now, right? The crisis is then, the problem is now, because what's happening is something called harvest and decrypt. Harvest now, decrypt later. So around the world, things like banking information and national security information and the codes needed to launch and program ballistic missiles in flight, all of that is being harvested now with the idea that as soon as an adversary can decrypt it, that becomes useful, even if it's information created today. Let's say that doesn't happen for 2 or 3 years. That's still incredibly valuable data to have. This is what makes the approach to Shor's so very important, and it's the kind of thing that gets attention. The other thing I would add to Jerry's point is a lot of the estimates for how long these things are going to take are sort of predicated on qubit counts. It's going to take this many qubits and so on. And as Jerry said, some things are happening. As we get better, we need fewer and fewer qubits. I've been involved in quantum computing for about 8 years, and I have watched that number for how many qubits are needed to implement Shor's drop every year for the last 8 years. The other thing that's happening is the algorithms are getting much, much better. We're writing tighter and better algorithms all the time. In conjunction with that, the software is getting better. There are some really talented folks writing software to optimize the number of qubits that we have available to us today.
So Jerry, on that note, I know that IBM is also exploring a lot of quantum safe cryptography. Talk to me a little bit about what you guys are doing and why this is also such an important issue.
Yeah, I mean, very much agree with all the points said here, right? I think the point is that cryptographically relevant quantum computers are coming. Algorithms will drive the resource counts further down. And the point is though that there are quantum safe encryption protocols that exist today. And to the point that NIST is pushing for adoption of new standards, maybe they need to move the timelines up, but I would say that everybody should already be thinking about moving to these quantum safe encryption protocols as soon as they can. Because there's no, obviously it needs to be a global shift, right? It's always an inertia problem in different industries to do something like this, but it needs to happen, right? Because the technologies are coming, algorithms are being developed that reduce resource counts, technologies are improving in terms of the underlying hardware, and it's more an inevitability of anything.
So I want to talk a little bit about the impacts of quantum. And as we get into that, Lamont, you work, as you mentioned, very closely in government sectors. What are some short-term wins that we could start seeing with regard to quantum?
So there are a couple. One of the close in, I hate the term low-hanging fruit, so I'm not going to use it. One of the closer in opportunities for us in quantum technology is really going to be in the area that Amanda is focused on around quantum sensing. The Defense Department, the intelligence community, others are paying a lot of attention to the work that's happening in that field because there are some really interesting developments just happening, I guess I would say. And so that's an area that we think will have immediate results. But as Jerry was saying a few minutes ago as well, I don't think the answer in the future is just going to be a quantum computer. It's more likely, especially in the next 5 to 10 years, it's going to be about hybrid workloads and what we can do shifting work between quantum computing and HPC and then understanding those results. It's not an easy fit today, candidly. We're working on the networking and the communications protocols and all of that to link quantum computers with high performance computers. We also need to understand how we share those workloads in a way that makes sense and we get meaningful results. As NYU announced here today, a lot of that is going to be university research to figure out the pieces of that puzzle, and then industry is going to design and build products around it.
So I was at IBM very fortunately about a year ago, and one of the things that we were talking about a lot was this hybrid environment. And I know that you guys are really pushing the envelope when it comes to a classical and quantum and AI environment. On that, are you seeing some of the pharmaceutical companies that you're working with or material science companies that you're working with really elevate that now?
Yeah, I think one way to think about it is think about the GPU boom from the 20 years ago, right? Where a lot of development in terms of usage came through scientific compute. We're co-locating these systems now with high-performance computers. In June, we launched a system in Riken next to Fugaku, the most powerful supercomputer in Japan. Just last week, we launched a system in the Basque region in Spain next to a supercomputer there. With RPI, we're exploring connections between their AMOS supercomputer and our Quantum System 1. The workloads that can be broken down, right, are really ones where now you can ask, how much of the supercompute time can I offload to the quantum computer for certain kinds of problems? And we're already seeing that for certain kinds of molecular structure investigations. Lockheed Martin has picked this up to explore, various molecules. The Cleveland Clinic has been looking at it. You bring up pharmaceuticals, right? Especially in modeling and simulation of molecular structure and chemicals. There's a real opportunity here because, just in terms of the raw amount of supercompute that's typically used, even moving the needle a little bit there economically can mean quantum advantage.
So I'm going to double down on that a little bit. And I get this question asked a lot. Is quantum going to replace AI?
It's not going to replace AI. If anything, it's going to both augment AI in certain areas for certain kinds of classification types of problems, but also I think AI is going to play a big part in the overall solution of problems with quantum, and people are already leveraging AI to help with how you translate problems into the quantum circuits, for example. So if anything, you need to think of it as not one or the other, but it really is a cohesive, everything comes together in this future of computing vision that we're gonna steamroll forward with all these different parts of our compute fabric.
I think one of your colleagues said, there's quantum for AI and then AI for quantum. And there's a little bit of a differentiation of those two, especially when it comes to programming these algorithms and making sure that we're fine-tuning things. So Lamont, I want to throw it back to you on workforce. And obviously this is a new ecosystem. It's being built out. There's handfuls of companies right now that exist out in there, in the various ecosystems around the world. What will it take for us, and what is the current path that we're on to develop this workforce?
this is an area of critical importance. It makes NYU super important for the future as we continue to grow this field and really develop a nascent industry for a couple of reasons. First, we'll talk about the roles that are needed, right? It's not all quantum physicists. We hire engineers, we hire product engineers, we hire hardware engineers, we hire software developers, we hire maintenance techs. If you walked through our R&D lab, you'd see people in bunny suits taking chips apart and rebuilding them. They're not quantum physicists. They're people who understand chip design. So we've got a lot of different skill sets that we hire for, and all of these are important. But that said, there is no mistaking the fundamental importance of quantum physicists for advancing the science of quantum technology. There just isn't. And here's a statistic that I use a lot when I'm meeting with government audiences. There are roughly 330 million Americans. How many people, on average, every year, do U.S. universities graduate with a PhD in quantum physics that are U.S. citizens? Anybody want to make a guess? Anybody? Throw a number at me.
100.
100. I hear that one a lot. What else? Anybody? Here's the number. I actually did this. I was curious myself. On average, every year, it's about 48 people. 48. Some years it's 41 or 2. Occasionally it's 50 or so. Generally, the average over the last 8 or 9 years is 48 people. That means there are only 48 quantum physicists who theoretically, no pun intended, could obtain a security clearance and work for the government in quantum physics. And many of them don't want to. They want to come up here and make a fortune. They don't want to work in a lab in Lanham, Maryland for GS wages. So we really, really need to focus on that and continue to drive those numbers in order for us to advance the science.
So I'm going to switch the conversation over to blockchain. And this is sort of a big topic at the moment, especially with Bitcoin prices and so on. But to sort of give a little bit of credit, Dimitri Green, our chief science officer, wrote a paper a few months back and talking about the vulnerabilities of blockchain and how quantum could impact that. Jerry, how does IBM Quantum really assess blockchain and a threat with quantum?
It mirrors the discussion earlier with Shores in the end, right? So the blockchain is securitized with elliptic curve cryptography, and it is also a target, right, for Shores-based systems, and breaking that kind of encryption that you would otherwise do with what we discussed before, right? And so blockchain is certainly, or Bitcoin is certainly a potential target, right, of quantum computing, and again, something which I would argue is also on that realm of should shift to different kinds of encryption standards sooner than later.
You want to follow up on that?
I do, because the threat here with blockchain is that, as I was saying earlier, the harvest now, decrypt later model, I think you can begin to see what the threat is there to blockchain transactions. Is it secure today? Yes, probably so. Is it secure later? Maybe not. Is today's transaction secure in the future? We're less sure about that. And what makes this especially concerning is, unlike Y2K, we knew when that date was coming. I worked on programs to prepare for Y2K. Well, that was obvious. All you had to do was look at a calendar to know when Y2K was going to hit. Nobody can look at a calendar and know when Q-Day is going to hit. And it makes it that much more important to begin to think about post-quantum cryptography now. We are. IonQ, about 6 weeks ago, hired a distinguished scientist named Marco Pistoia, who led JP Morgan Chase's global quantum efforts, in addition to a number of different roles, for just that reason. When I joined the company 3.5 years ago, we weren't really thinking about post-quantum cryptography necessarily. We knew it was there. We certainly weren't thinking about the impact to blockchain. We are today.
And one of the things that Marco did was help develop one of the truly first random number generators. And that has such a huge, profound impact, especially when we start to look at cybersecurity and other formats. So closing question for both of you, what is the most exciting part, and what are you most looking forward to when it comes to quantum? And then we'll open it up to some Q&A, so think of some questions.
Yeah, I mean, I think what's exciting to me is just the pace at which things are going, right? We certainly at IBM, and you see throughout the industry, a lot of emphasis for us certainly on roadmaps and hitting targets in terms of pushing the envelope of performance of the underlying technology. We talked about quantum circuits. Basically, it's all about being able to run larger and larger quantum circuits, both in the number of qubits, also in the complexity of the types of circuits that you run. And we have this mapped out all the way through into 2033, looking ahead in terms of keeping us honest of hitting these various targets every year after year. And to me, that's very personally rewarding to be able to work on this type of technology, but also to be able to deliver it as something that is part of a computing ecosystem that everyone can use.
And really quick, Lamont, before you start, Jerry, explain to me how cold the chip is that you guys have.
So the superconducting technology gets cooled down to 15 millikelvin, 0.015. But I think what's phenomenal about that is that you can get that cold with basically plug it into the wall turnkey systems that are commercially available and can run for years on end. And it's not a technology that you need to be afraid of, right?
So that said, one of the things, I was on a call with a electricity provider, let's just say a few weeks ago, and they were less enthused about quantum because they felt like it was going to start replacing some of the data centers that were out there, or augment some of the power of all of these GPU clusters out there, and require far less energy.
Drop in a bucket compared to the GPU.
Yes, yeah.
GPU footprint, right?
Lamont.
Yeah, I would say the same thing. Our power usage, swap overall, is far lower than with most HPC systems. And I'll relate that to a conversation I had at Oak Ridge National Lab when Frontier came online in 2022. We were touring down there, and they explained to me that the only limit to the size of Frontier, by the way, that was when it went live in 2022, I believe the world's first exascale computer. And they explained to me that their only limitation on the size of Frontier was power consumption. Had it been any larger, this is no exaggeration, they would have needed to build a power station fully dedicated to that one machine sitting in a lab just to power it. Conversely, quantum computing generally uses orders of magnitude less power. We could essentially plug a quantum computer into a couple of wall sockets and run it. That has such promise for the environment and for the world going forward, and for all of the things that concern us, right, about climate change and these things. This is what makes quantum computing maybe a national security concern, but also a tremendous gift to the universe.
All right, so I would like to open it up to any questions that you guys might have. Just a few. Yep.
Hello, so I have a question about the roadmap. We know that IBM is a quantum computer with more than 400 qubits.
Go ahead.
Okay, so a question about the roadmap. I know that IBM has a quantum computer with more than 400 qubits, but I'm curious, where can I, as a common user, access this quantum computer? And a similar question for IO2, what can we expect in terms of the number of qubits and fidelity in the upcoming years?
Yeah, so to address your question, so we have multiple 100 plus qubit systems available today, right? There are commercially available systems are the Heron processor today. We've had demonstrations of other machines beyond the 100 qubit number, right? With Osprey a few years ago at 400 qubits and Condor at 1,000 qubits. But those were technology demonstrators, so those weren't fully deployed.
And really quick, explain qubits versus logical.
Well, so these are all just qubits, right?
Yeah.
So these are all physical qubits, right? And maybe just so everyone understands, right? The qubits are really where you're running these quantum circuits, the size of the register of the circuit that you can run on. Over time, as we build up towards error-corrected devices, you're going to have, when you're talking about millions of qubits or hundreds of thousands of qubits, you're using those to then encode logical qubits, okay, in error-correcting codes, because that's the ultimate solution for handling noise in these machines. And so think of it as like, you need your CD music, right? It has error correction codes so that when you ride a bike, your music doesn't skip. You need a similar kind of error correction code so that you can avoid the errors that can occur in some of these types of devices, these quantum devices. So today we host 100 qubit machines. We're scaling them with long distance connections, these L couplers over the next few years that will let us get to register sizes of 1,000 qubits over the next few years. But then ultimately we're driving towards error-corrected logical qubits in 2029. That'll be 200 logical qubits, but from a gate circuit depth perspective, that'll be 100 million gates compared to 5,000 gates today.
So currently, if one were to go online, create an account, as I was mentioning earlier with IonQ, the machines that are available in our data center for public use are 37 roughly qubits, fairly small. And what I encourage people to do is try the different machines that are available online. Try an IonQ machine with 37 qubits, see how it works. If IBM is available to you, try that as well and see what works for you. Try different modalities to see which ones best meet your needs, and then go with that. The machines that we're developing today, if someone came to me after this and said, I want to buy a quantum computer, how many qubits would be available? The answer is 256. It'll take us about a year to build it. And that would be available for, if someone were buying one right now.
And on the investment side, I think we're really excited when we talk to companies, especially on the application side, that are simulating right now or are using your guys' systems right now, knowing that in a couple of years from now, they're going to have a significantly greater compute power. But it's going to take them a couple of years to get their program accurately built, and what we're most excited is that their advantage at that time period in a couple of years from now will be far greater than any of their other competitors that exist, because they're not going to have to rewrite their code, for one thing, and the second part is they're not going to have that tech debt. And I think that's really just an amazing time period that we have right now on being able to advance a lot of the quantum applications that will be developed over the next couple of years. Another question, anyone?
Can I make a comment about quantum applications?
Sure.
This is a really exciting area, and it's one that all of us think about, but none of us can really properly envision. And there's a reason for that. Imagine if I had come to you, let's say you're all managing a fund, and I came to you and said, I'd like $1 billion in investment, and you said to me, what are you going to do with it? This is what Matt does, he answers these questions. Lamont, what are you going to do with my $1 billion? And I said to you, I'm going to take $1 billion, and at the end of it, I'm going to give you a phone that you can use to call a taxi. Would you give me $1 billion? No, you wouldn't. Of course not. Would you give me $1 billion if I could give you Uber?
Sure.
Absolutely. It's an application no one could have thought of when they bought a cell phone, and a flip phone, right? A Motorola or a Nokia, and stuck it in their pocket. But imagine if you could have envisioned what could be done with an Uber. We're at that point right now. We're at that inflection point now with quantum technology of beginning to unlock applications and opportunities that, as we sit here tonight, no one can envision. you said what's exciting? That's what's exciting.
Any last thoughts?
I mean, I fully prescribe to that vision, right? I think, there's so much to be done in the space of application algorithm development. It's, and to your point, especially with open source platforms that are out there, like what we have in Qiskit, it's so easy to get involved and engaged and to actually use these machines, right? So, through Qiskit, you can actually access IBM hardware, you can actually access IonQ hardware, right? That's really a big part of the ecosystem development, much like we saw again in terms of GPU development in the past, right? Driving scientific compute, driving applications and algorithms. The time is ripe right now, and it's better to get started early than to wait.
On that note, thank you guys all so much for participating in